Welcome. Problem number 2. Problem number 2 among these 26 problems. Now problem number 2. A model rocket of 1 kilogram mass is attached to a horizontal spring with a spring constant of 6.0 Newton per centimeter. The spring is compressed by 18.0 centimeter and then released. The intent is to shoot the rocket horizontally, but the release mechanism fails to disengage, so the rocket starts to oscillate horizontally. Ignore friction and assume the spring to be ideal. What is the amplitude of the oscillation? What is the maximum speed? What are the rocket speed and acceleration when it is 12.0 centimeter from the equilibrium position? We tried to draw the picture of our problem. The rocket is this. We are given this amplitude from here to here. This is amplitude. We are given also the spring constant. The spring constant here, K. We are also given the spring is compressed by, which is the amplitude, the mass of model rocket. This model rocket has 1 kilogram. Now let's find amplitude of the oscillation. Amplitude of oscillation is already given. From this equilibrium position to this maximum displacement, from this equilibrium position in negative direction here to this maximum displacement, this is called amplitude. So the amplitude equal the amplitude is amplitude is 18.0 centimeter. B. What is the maximum speed? The maximum speed. We have maximum speed at this equilibrium position. At this equilibrium positioning, the x equals 0. We use conservation energy principle to find the maximum speed. The law of conservation energy means that total energy equal kinetic energy plus potential energy. Total energy. See in introduction, we have already a video explaining these ideas: kinetic energy, V plus half potential energy. Remember, we have the maximum velocity. The maximum velocity occurs when x equals 0 at equilibrium position. At equilibrium position here. This equilibrium position, you have Vmax. Vmax, well, x equals 0. Zero displacement here. Using those concepts, we find that this conservation law of energy becomes like this. Vmax here, maximum velocity, plus 1/2 k, 0 here, because at equilibrium position x equals 0 when we have maximum velocity. Now let's solve for maximum velocity. We get maximum velocity equal k over m root times amplitude. Solving this equation, we find the maximum velocity. Replacing, we get k is already given, mass is given, we have 6 Newton per meter over 1 kilograms times 1/0 centimeter we get here. Remember to convert centimeter to meter. Now converting this to meter, you get this. Now let's write the converted data here. The converted measurement like this. Then you get 4.4 meter per second. The maximum, the required maximum velocity equal to the maximum velocity equal equals to 4.4 meter per second. C. Let's now solve C. What are the rocket's speed and acceleration when it is 12 centimeter from the equilibrium point? When now it is 12 centimeter from the equilibrium point. Let's solve C. When the speed at displacement of 0 cause we have 0.0 centimeter, which is equal to meter, we get the relation of the speed by applying again the energy conservation. Total energy equal kinetic energy plus potential energy. Let's write this relation like this. Kinetic energy. Here we don't use mass because we are no longer on the equilibrium position. We have the position here 0.120 meter plus k square. Here we are given the position. We don't use equilibrium position. Now let's solve for V. Solving for V, we have here these halves cancel out. Solving for V, this is a simple algebra only. Negative. Now trying to cancel this negative, we get rearranging, we get mv square equal k square negative square. Solving for V, I factor this k here, a square x square V equal square root k over m amplitude square minus the square of the given displacement. Now replacing, you get, try to put the given value, and 0 over 1 kilogram times 0 amplitude, okay, this square over the given displacement square, you get 3.3 meter per second. The speed and acceleration. Now it's time to find the acceleration. It's time to find acceleration. Acceleration when x equals 0 to 0 meter. Here we use Newton. We use Newton second law to find the acceleration. Let's try to apply the Newton second law, which says that force equal mass times acceleration, which is equal constant spring, like this. Yes, trying to solve for A, you get K over M. Here I have negative sign here. Good. Times X, you get negative 6.0 times 2 Newton meter over 1.0 kilogram times the displacement, the given displacement meter, you get negative 72 meter second square. Let's here find the magnitude of acceleration. This is acceleration as a vector quantity. Now the magnitude, let's find this magnitude of acceleration. You find only, let's focus on the magnitude. Find like this. The acceleration we know is always negative, or is always in negative x to, it's in negative point to negative x direction, regardless of whether the object is moving to left or to the right. It's always in your opposite direction with respect to the displacement x. Dear friends, Thanks for watching. I hope I was clear in this solving this problem. Now next time we will solve the problem number 3. Thank you for watching.